Hello and welcome to the second video on section 1.8, continuity. In our first video, we developed a graphical understanding of continuity. From our definition, a function is continuous at a point if the limit and actual value both exist and are equal. In this video, we get down to the nuts and bolts, how we can determine continuity for a function without graphing it. Everything in this video builds on two things: the definition of continuity, and the limit laws from section 1.6. Now might be a good time to review section 1.6. Most of our results about continuity jump right out of the limit laws. Take, for instance, the sum and difference limit law, which says that if the limit exists, then two functions can be combined before or after the limit is taken. A similar law holds for continuity. Suppose f and g are continuous at a. Using our sum and difference limit law, we use the fact that f and g are continuous at x equals a to determine that the limit of f plus or minus g as x approaches a is f plus or minus g at a. That is, if f and g are continuous at x equals a, then f plus or minus g is continuous. In the same way, the limit laws lead to new rules which allow us to make new continuous functions out of functions that we already knew are continuous. You might want to pause for a moment to read through the list. Like limit laws, we have a constant multiple, a sum and difference, a product, and a quotient rule for continuity. If you really want to do things right, you might try justifying the continuity laws from the limit laws, in the same way we justified the sum and difference continuity law a moment ago. It is not critical that you memorize these, but you should be generally familiar with them. We can build new continuous functions once we have a continuous function, but what are some continuous functions? The functions which are the building blocks for the majority of functions we'll use in this course are continuous on all points in their domain. Our building blocks will be powers, roots, and trigonometric functions. As these building blocks are continuous on their domain, now might be a good time to review domains, especially of trigonometric functions. Take, for example, the function f. We can break f apart into its basic building blocks: x plus 7, x minus 2, and the square root of x. X plus 7 and x minus 2 are continuous at all points, as they are polynomials, and polynomials have a domain of all real numbers. The square root of x has domain x greater than or equal to 0, therefore it is continuous on the interval from 0 to infinity. In determining which points are continuous, you begin with a list of all real numbers and remove points which are discontinuous. Since the domain of the square root of x is 0 to infinity, all points outside of this interval will be discontinuous for f. Since the domain of the square root of x is 0 to infinity, all points outside this interval will be discontinuous for f. As division by 0 is undefined, when x is 0 or 2, the denominator will be 0, so at these values, f will be discontinuous. The remaining values, 0 to 2 and 2 to infinity, excluding 2, are continuous by the quotient and product continuity laws. All of these values make the building blocks continuous. You should now be able to identify points in which a function is continuous from the equation alone.